So a particle has initial displacement S0 equals 3, 5, given that U is 1 minus 1 and A is 0 minus 2. Find the displacement in vector form of the particle at time t equals 4. Okay, so as like a normal Suvat equation, I would just write down the variables we have to start with. So U is 1 minus 1. V we don't have. A is 0 minus 2. T is 4. Now, don't get confused. Notice how this says S0. It's not S. So we're going to imagine we don't have this for now. So we don't have it for now. We're just going to use S equals UT plus a half AT squared with the information that we have here. So UT, so we're going to have 1 minus 1 times 4 plus a half of A, which is 0 minus 2, times 4 squared. So you can work this out like normal, doing each component separately. So 1 times 4 is going to be 4, minus 1 times 4, minus 4. Plus a half times 0, so 0. Half times minus 2, minus 1, times 4 squared. 4 squared is 16. So tidy this up a little bit more. We're going to have 4 minus 4 plus 16 times 0. Well, that's going to be 0. Minus 1 times 16, minus 16. And then add the top components, add the bottom components. We're going to end up with 4 minus 4 plus minus 16, so minus 20. We're not quite done because this is the point where we take into account our initial displacement. So this is our displacement during the time period, but obviously if we're already slightly away from the origin, our final displacement away from the origin needs to take into account how far we were away originally. So let's do 4 minus 20 plus our initial displacement, which was 3, 5. So 4 plus 3, 7, minus 20 plus 5 is minus 15. And we're done. So this is our displacement at time t equals 4 in our normal notation, our vector notation. So a particle's acceleration a equals 2ti plus t squared j. It is initially stationary at the point s0 equals 3i plus 3j. Find an expression for its displacement vector s at the time t. Okay, so to go from acceleration to displacement, first we're going to have to go to velocity. So we're going to integrate acceleration to get velocity because the integral of a with respect to t is v. So let's integrate this. Well, the integral of 2ti plus t squared j with respect to time. So you don't need to really worry about the I and j, just worry about the coefficients in front of them. So integrating 2t, well, we'll get t squared, and then I'll just add the I after. Integrating t squared, we're going to get t cubed over 3j. And then, obviously, in pure, you have a plus c. In this case, we do still have a plus c, but because it says initially stationary, so it's not moving, then the initial velocity, not v, so u0 is 0. In this case, we need it in vector form, so it would be 0i plus 0j. Obviously, if we add that on here, then it makes no difference. So let's just get rid of that. Okay, so this is our velocity. And then remember the integral of velocity with respect to time is displacement. So we're now integrating this. So integrating v with respect to time. Well, again, integrate the components separately. So the integral of t squared, we've already done that once, t cubed over 3 I, and then integrating this, increase the power by 1, divide by it, so we'll have t to the power of 4 over 12, and that's going to be the j component. And then again our plus c. In this case, if we were starting from the origin, the plus c would be 0. In this case it's not, because it's s0, so we add this on. So we'll add 3i plus 3j. And again, just add the I components, add the j components. So we're going to have, I'm going to open some brackets. So we're going to have t cubed over 3 plus 3 I, and then plus t cubed, t to the power of 4, not t cubed, over 12 plus 3. And then that's going to be the j component. Now, you don't need these outer brackets. You could just write it as the inner brackets times I, and then the other bracket times j. I've just put them there for the sake of trying to keep it a similar notation to like that.